Alright, so let's go on with this tutorial, and this is problem number 6. In problem number 6 I have been given this graph, and I have been also said that this is the process that has been carried out from A to B is a single stage expansion. Single stage expansion I have explained you before in previous problems, in probably question number 3. So it's a single stage expansion, and I've been asked to, or rather you have been asked to calculate work in Joule. So you go about calculating work in Joule for this problem. This is a PV graph, and it's very easy to calculate PV work from a PV graph. Now this is a single stage expansion, so it will be a fast expansion. It is not a reversible process, rather this is an irreversible process. So every formula that we have memorized up till now is not going to be of any use. Rather we will have to solve it very conceptually using the very basic fundamental formula for calculating work. Now as you can see, all these dotted lines shown in this graph, I have not joined A and B by any of the path, because I cannot do it so, because it is a fast process. So at any moment during the process, pressure is not completely defined inside the volume, inside the system. So I cannot show any point on this graph, because if I plot any point, suppose for the sake I show the process like this. When I show a process like this, that means I am very sure that at this volume the pressure was this. So I have a unique pressure corresponding to every volume, but that is not true. What happens is, when you expand it very fast, so the piston comes up very fast, and then the gas rushes in to fill the vacuum created by the piston. So the pressure inside at the lower level, so the gas molecule at the bottom will not be aware that the piston has moved up and we have to run to fill up the space. So these gases will be moreover towards the bottom, and the gases towards the upward region will rush first, and then the gases towards the bottommost region. So there will be more density at lower region and less density at higher region. So there will be a pressure difference, and there will be different pressures at different point inside the container. So absolutely we cannot define a pressure at every point. So when you have a very fast kind of process, then the pressure of the whole system is not uniquely defined. So I cannot have a path showing by a complete line a very fast process. So this A and B haven't been joined by any line for this reason. But still, nevertheless, you have to calculate work in this process. So to calculate work, let's go on to the basic formula. To calculate work, integrate PDV. Integral PDV is the work. So here the pressure would be constant, because it is a single stage expansion. That means whatever the pressure finally you have, you make that pressure equal at the beginning of the process. So what exactly you will be doing here is, so you will be having some kind of clamp, and then you will be having some weight here. Okay, so if you remove this weight all of a sudden, then the gas, this piston, due to the internal pressure of the gas, will run upward, and during that whole run upward, the pressure would be on the piston constant. That will be the atmospheric pressure, because from inside what will happen is, when this piston, suppose this piston moves up a little, when this piston moves up a little, gas will be unaware of this fact. So there will be a kind of vacuum in this region, and then when these gases will see the piston is moving up, then these gas will come up to fill up this vacuum. So actually from the lower side, the piston will not be having any pressure. From the up, it will be having some. So it will be running up, and the resistance that it will be having is the external pressure. So the pressure on the piston technically will be constant throughout the process, and that will be the final pressure that it will be going to have here at this point. Okay, so my system was at A, it went to B, it has some pressure. So since it is a single stage expansion, So since it's a single stage expansion, the final pressure would be the same, or the initial pressure throughout the initial pressure for the process will be the same as the final pressure in that system will prevail. Alright, so if we have to calculate work in a irreversible process, then we cannot use any of the formula, but fortunately the question that will be asked in the problem will be of such nature that the pressure in those process will be constant. So what you can do is you can bring this pressure out and then you can only integrate dV. So your life still is very easy. You can integrate this integral, so not much of a trouble. So what pressure here we have is 1. So even if I have this concept, there is high chances that I will end up in a wrong answer, for the reason I'll tell you. The pressure is 1, so you bring it out of the integral and you integrate volume. So integral dV is delta V, that means V final minus V initial. So 1 into V final minus V initial. Final volume is 4 minus 2, that is 2, so it will be 2 joule. The answer would be 2 joule. Alright, so we move on to the next problem. When I say we move on to the next problem, and any of you who didn't shout, "Hey wait, that's a wrong answer," is not attentive enough. You must have shouted, or you must have actually felt uncomfortable because I solved it. The procedure was right, but technically I did some mistake. I did some mistake in units. Now you have to remember, whenever you want a SI unit, then you give SI unit to every quantity that is there in your expression. Now joule is the SI unit of work. When I want SI unit of work, I need to put in SI unit of everything that is used to calculate that work. Here we have pressure and volume. The SI unit of volume will be liter. Volume has been given in liters, so not a problem. 4 minus 2, that is good enough. But for pressure I have used 1, and 1 is in atm, and atm by no way is the SI unit of pressure. The SI unit of pressure is Pascal, so I need to convert this atm, atmosphere, into Pascal. So I need to convert it, then only I'll get joule. So this is not actually 2 joule. If you write it as 2 atmosphere liter, it is 100% correct. So it is 2 atmosphere liter but not 2 joule. If you have to report your answer in 2 joule, you must convert this atmosphere into Pascal, and the conversion factor would be 101.325. This is good enough to use. So when you do this, you will get 202.6 joule. So this is the work done by the gas, or work done. If you have to simply say work done, you will have to add minus sign according to the sign convention, because actually this is the expansion. Gas will be doing work, energy will be consumed, or the gas will be doing work at the cost of its own energy. Its internal energy will decrease, and according to the sign convention, anything that decreases the internal energy is negative. So work done is negative because work is done by the gas. So if you say work done by the gas is 202.6 joule, it is 100% correct. But if you say work done is 202.6, then it is ambiguous. Work done is, if you say positive, then it is implied that work is done on the gas. When you say work done is, then you have to say work done is minus 202.6 joule, or work done by the gas is 202.6 joule. Alright, that's how. If you are explicitly mentioning that work is done by the gas, then you can say work done by the gas is 202.6, or else you can say work done is minus 202.6 joule. Minus will simply imply that work is done by the system, and in my system there's gas. Alright, so this kind of problem will be there in whatever competitive exam you are going to sit on. in CBSE boards they are not going to ask this, but in competitive exams surely definitely there will be some problem on irreversible process like this in which none of the formula will fit in. So you have to understand the basics. This integral PDV is going to give you all the marks from thermodynamics, at least from the first law, at the stage up till the stage of first law. So we move on to the next problem. So this will be question number 7, and question number 7 again is going to be a easy problem. In question number 7, again I'm going to give you a PV curve and you have to give me the work done in the process. This will be easy. Now this is a graph that has been given to you, and this is the pressure axis, this is the volume axis, and I have started from A. Suppose I have started from A at this point, went to B, then C, and back to A, and in this cyclic process I'm asking you the work done. So what will be the work done in the cyclic process? Then we have seen this before actually, the area under the curve. And when you have a cyclic process, then the area under that cycle actually provides you the work, the magnitude, and the sign you have to look for. If you're starting from A, then A to B is isochoric process, work done will be 0. B to C, the area under BC curve. This is BC. BC is a straight line, and whole this area will be included in that. This is expansion, so work done will be negative. And then C to A, this is the area, and this area will be cancelled out. So whatever area you will be left with will be only the area which is inside this cycle. Okay, that's how it is. And the area will be, and the net work done will be negative. So we have talked this before. We have talked about this before, that if it is a clockwise cycle, then the work is negative, and if it is an anti-clockwise cycle, work done is positive. So we have confirmed upon the sign that the work is going to be negative. And let's talk about the magnitude. The magnitude will be the area of this cycle. This seems to be a triangle, so area will be half base into height. Base, you see, it's 2v from V1, from V1 to 3v1. That is 2v1 is the base, and height is 5p1 from p1 to 6p1, that is 5p1. That gives you 5p1 v1. That's the work. Alright, so PV graph is going to be a lot helpful in calculating work in thermodynamics. Let's move to problem number 8. From here we will increase the toughness level of the problem. Problem are going to be a bit more intricate from now. Again, I give you a pressure volume curve. Now this is a pressure versus volume curve, and I have specified temperature at 3 different points. This is A, B, and C. Now there is no information provided about the pressure and volume at these 3 points. Only temperature at these 3 points has been specified. The other information that you have from here is this pressure volume curve is about of a heat engine. You don't have to bother about it. Heat engine is going to come in thermodynamics second law that will be subsequently studying, but nevertheless this is a curve of a heat engine which carries 1 mole of a ideal monoatomic gas, and what you have to calculate is the amount of heat added in the process AB. This is the process AB, and suppose the cycle goes in a clockwise manner like this. So what you have to find? You have to find QAB. What amount of heat has been exchanged in the process AB? So we have to find the amount of heat exchange in the process AB, and what we need to find out the work in 5 processes. We know thermodynamics first law. Apart from this, we know other small things like ideal gas equation. We know the formula for change in internal energy, that is NCV delta T, and other fundamental things from the ideal gas and real gas equation that we have done in the gaseous state chapter. So if when we move from A to B, it seems to be an isochoric process because volume is not changing. This volume remains constant throughout the process from A to B. So in this kind of problem, always and always you will be requiring thermodynamics first law. So it's better to write thermodynamics first law on your paper. Now thermodynamics first law is delta U is equal to W plus Q. Whatever work you do, whatever heat you give, that will sum up to the change in internal energy. Now in process from A to B, you have been asked to calculate heat exchange in A to B. So using thermodynamics first law, W becomes 0. W becomes 0 because volume is not changing, right? So there is no change in volume. dV is 0, so PdV is 0 as well, so work done is 0. So if you calculate delta U, you can calculate Q, easy, and you can calculate delta U. You can calculate delta U by using this formula. Delta U is equal to NCV dt or NCV delta T. Now I might not have told you this formula, or we might not have discussed this formula before, but I expect you to know this formula from the chapter gaseous state, and in case you haven't studied gaseous state, do not worry about. In the latter course of this chapter, I am going to discuss this formula. We are going to discuss CV and CB, and we are going to discuss their significance. We are going to compare them. We are going to see the relation between CB and CV. So this eventually will come up. So don't worry yourself over this. Don't bother yourself over this. But know this, in case you don't know. Delta U is equal to NCV dt. For the sake of solving this problem, let's believe in this formula. So we will calculate delta U, and then Q will come out very naturally. So CV, now this information has been provided in this chapter in this question, as I told you that this is a monoatomic gas. Now again I'll be using some information or concept from gaseous state. For a monoatomic gas, CV is equal to 3/2R. Now how it comes, it's a different thing altogether. We will discuss it how it comes, but for the now, believe in me. I hope you believe in me. Believe in me that CV is equal to 3/2R for a monoatomic gas, and it has been given that the amount of gas is 1 mole, so N will be 1. Alright, N will be 1, CV will be 3/2R, and Tt, what is the change in temperature? Temperature here is given 300 Kelvin, there it's given 600 Kelvin, so change is 300. Everything in SI, whatever comes will be in SI, right? Alright, so here it's easy. You cancel this out, it will be coming as 450R. Now if you in most of the time in the option it will be given in the form of 450R. If it is not, then you have to put the value of R, and you will put the value of R as 8.314 joule per Kelvin per mole. So this 1 is in mole, this is 300 is in Kelvin, so per mole per Kelvin will get cancelled out, and 8.314 into 450, and joule will be the unit. Alright, so the value of R that you will be using, in case the option do not provide you R, then the value of R that we'll be using is 8.314 joule per Kelvin mole, right? So this Kelvin and mole will get cancelled out and joule will remain. So this thing you have to remember. In joule per Kelvin mole, the value of R is 8.314. There are other values of R in calorie. It's around 2 calorie. That we'll be discussing when we will discuss Cp and Cv. Now for time being, delta U is 450 R. Now delta U is positive because temperature has increased. So if temperature has increased, that means kinetic energy, internal energy has increased, and there hasn't been any work done. So if internal energy has increased, that will come through heat. So the heat exchanged will also be 450 R. That will be equal to change in internal energy. So this part of the question was simple, easy. They have been asking what was the heat exchange. Heat exchange is 450 R. Alright. Now for AB, this was easy. For AB, so Q at AB, but they were asking that is equal to 450 R. Alright. Now suppose they ask for AC or CA. Now for AB this is done. If the same thing is asked for CA, then what will we do? If suppose they were asking Q for CA. For Q, if they are asking CA, then CA process, look at CA process. In CA, pressure is remaining constant and volume is changing. Now the change in volume you don't know, because the volume at C and the volume at A has not been given. What has been given is all you have been given is temperature. Now again, definitely you are going to use somehow or the other thermodynamics first law. So let's write thermodynamic first law. Thermodynamic first law is delta U is equal to Q plus W. And let's see, we have to calculate Q. So somehow we must know W and delta U. W is work done. So we have to find out work done, and we have to find out delta U. Now delta U you can find because temperature has been given. Here you have 450, here you have 300. So temperature, if you know, then you know delta U, because the formula for delta U, you know, the formula for delta U is NCV dt or NCV delta T. N is 1 mole, Cv will be 3 by 2 R. Cv is equal to 3 by 2 R. If you don't know, please memorize this, and later on we will see the explanation of it. Okay, so Cv is equal to 3 by 2 R for a monoatomic gas. For diatomic gas it will be 5 by 2 R. Triatomic gas it will be a different value, 7 by 2 R. So for monoatomic ideal gas, Cv is equal to 3 by 2 R dt. The final temperature is 300. The initial temperature is 450, because we are calculating Q for CA. CA means from C to A. So the change in temperature, change is always final minus initial. So change is minus 150. Alright. So this is going to give you minus 225 R. So delta U we have calculated. Now what we have to do is we have to calculate W. When we calculate W, then we know delta U and W, so we will know Q. So W, like, what is W? Work. What is work? Work is always integral PdV. So if you have to calculate work, W is equal to integral PdV. Pressure is constant because it's an isobaric process. The pressure will come out of integral. And how much is pressure? We don't know how much is pressure. So whatever it is constant. Integral PdV is delta V. Delta V is what? V final minus V initial. So PV, PV final, PV is equal to nRT because it's an ideal gas. We know PV is equal to nRT. So I can replace PVF as nRTF. TF will be final temperature, and PVI by nRTI. TI will be initial temperature. So this can be written as nRTF minus TI. Alright. And TF minus TI we know, don't we? TF minus TI is how much? Final temperature is 300, initial temperature is 450. So this is equal to minus 150 R. Right? This is equal to minus 150 R. but I'm a little sorry, you must have identified my mistake. W is not equal to PDV. W is equal to minus integral PDV to make it compatible with the sign convention. You know, in some books they may use integral PDV, or in physics they use integral PDV, but in chemistry our sign convention is such that to make it compatible, because you see, you know, volume is decreasing, and we have decided then when there's a compression in the system, whenever there's a decrease in volume, then work is done on the system and we consider that work to be positive. Just to make it compatible with our sign convention, we make the formula minus integral PDV. So all this minus will be carried over, and this minus will become plus. So actually the work done is positive and it should come 150 R. Okay, now Q we know, Q will be delta U minus W. So delta U is this and W is this, we know Q. Q will be how much? It will be minus 375 R. This will be the answer. So the heat exchange in process CA will be minus 375 R. Alright, let's move on.